Okay, let's do an example of calculations with simple harmonic motion. This example is in the notes. We have a frictionless surface with a horizontal spring. Sketching it here, and a block at the end of that spring, and the block is pulled back a distance of 10 centimeters from the equilibrium position. So here I'm indicating the equilibrium position of the spring. That's where it would be if there was no stretching. Let's move that down just a little bit and resize a little bit so everything fits. And we are told that it is stretched out by a distance of 10 centimeters, which is 0.1 meters. And we're also told that the mass of this block is 500 grams, which is 0.5 kilograms to put it in proper units. And we are told that it's stretched back there, and after it is released, it passes through the equilibrium position at a speed of 1 meter per second. And so that tells us what the maximum velocity is. At 1 meter per second. And the fact that's, sorry about the handwriting there, and the fact that it is displaced a distance of 10 centimeters from the equilibrium position and then released from rest at that position tells us that A is equal to 0.1 meters. So we have that from the setup of the problem. And we have V max equals 1.0 meters per second, also from the setup of the problem. That is its speed passing through equilibrium. Because we remember that for simple harmonic motion, the speed is zero when the displacement is at the maximum value. The acceleration is also at the maximum value when the displacement is at the maximum value, but the velocity is at the maximum value when the displacement and the acceleration are both zero. Acceleration is always going to be going in phase with the displacement because the acceleration is due to the restoring force, and the restoring force is proportional to the displacement. That's the condition for simple harmonic motion. The only difference is a sign difference because the restoring force is opposing the displacement. It's trying to bring it back to the equilibrium position. So part A of this example asks us to compute the period of oscillation for this thing. And there's no friction up here. I should point that out here. There's no friction. Okay, so the period T is what we're looking for, and we're given V max is 1 meter per second, and we know that V max is just A times omega, which is A times 2 pi F, which is A times 2 pi over T, because little f is 1 over T. So we can just calculate the period directly from that without having to do anything more complicated. Just rearranging this equation for T, we get T equals A times 2 pi divided by V max, which is 0.1 meters times 2 pi divided by 1.0 meters per second. That gives us seconds in the end, so 0.1 over 1 times 2 pi is just 2 pi times 0.1, or t equals 0.628 seconds. So that's part A for that example. It's pretty straightforward. Let's take a look at the second part of the problem. The second part of the problem is, what is the block's speed where the spring is compressed by 5 centimeters? So what is V when spring is compressed by 5 centimeters? Let's sketch that just so we're sure we're all talking about the same thing. It's just a wall and the floor here, okay? What color did we make our spring? Blue with a red block. So now the spring is compressed. Here's the block. And the equilibrium position is over here. And this distance is 5 centimeters. And it's not telling us enough information for us to know left or right, and it's not asking that. It's just saying what's its speed. And so this could be on its way to compressing all the way to be a full compression, which would be 10 centimeters, because it's going to compress it as much as it was stretched originally, or it could have already compressed it by 10 centimeters and be on its way back to the equilibrium position. So we don't know whether this block is moving left or right, but it doesn't matter. It'll have the same speed at that location, regardless of whether it's on the part of its oscillation moving to the left or the part of its oscillation moving to the right. So our expression for speed is minus Vmax times sine of omega t, which is minus Vmax times sine of 2 pi little t over big T. We just figured out big T. What we don't know is what time to put in there. We do know Vmax, we just figured that out from the setup, is 1 meter per second. And we figured out the period T is 0.628 seconds. But in order to get the speed at this location, we need to know T when X is 5 centimeters. And this thing is completely symmetric. So fortunately, in this particular case, I'm not going to need to worry about plus or minus signs for any of this stuff. In other words, it would be the same answer if X was 5 centimeters on the other side of the spring and it had been stretched by 5 centimeters instead of compressed by 5 centimeters. At any rate, our expression for the position is X equals A times cosine of 2 pi little t over big T. Well, what we're looking for is the value of the time when X equals 5 centimeters. So we've been doing everything in meters and meters per second, so I'm going to convert this 5 centimeters to 0.05 meters. So that gives me 0.05 equals A, which is 0.1 meters, times cosine of 2 pi little t over big T. And just to be, not have any round off errors, remember that big T was just 0.1 times 2 pi. I'm just going to write that in here instead of 6.628 so that my 2 pi's cancel out. So big T is 0.1 times 2 pi. Okay, so then my 2 pi's cancel, and I have 0.05 equals 0.1 times cosine of t over 0.1. Okay. Now I want to solve for t. It's buried inside this cosine. So we have to remember our trig. We're going to be doing an inverse trigonometric function here. So I'm going to rearrange this equation. I'll divide by 0.1. I'll move the cosine over to the left, just going to flop it around. So I have cosine of t over 0.1 equals 0.05 over 0.1. That's just a half. Okay, so I did several little algebraic steps there, divided both sides by 0.1, and then swapped which side of the equal sign everything was on. Now, to undo the cosine, I take the inverse cosine. So I take the arc cosine, a cos, which is the same as like sometimes written that way, of both sides, and I get t over 0.1 equals inverse cosine of 0.5. So now I have to get my calculator out and calculate that, and might be pay attention to whether my calculator is set up in degrees or radians. So inverse cosine of 0.5 is 1.047 radians. So I have t over 0.1. Let's just write it again, just to be careful. 0.5 here. T over 0.1 equals 1.047 radians. And t then equals 0.1 times 1.047 seconds, because remember, this 0.1 was part of the overall period, so that's where our units of seconds come from, so we cannot have this be in degrees. So your calculator needs to be set for radians when you do this function here. Make sure you're in radians. So 0.1 times 0.1047 is just going to be about 0.105. Don't need a calculator for that. T equals 0.105 seconds. And now we can go back and calculate the velocity. V equals V max times sine, V equals minus V max times sine of 2 pi little t over big T, and V max we had already calculated was 1 meter per second. Actually, we didn't calculate that, that was given to us. So it's 1.0 times sine of 2 pi times 0.105 divided by big T, which is the period. And again, remember that big T was 0.1 times 2 pi. So I'll just leave that in there again so that my 2 pi's cancel out. And that gives me V equals minus sine of 0.105 over 0.1. And that's got to be entered in as radians. So let's calculate what that number is. Sine of 0.105 over 0.1 is 0.87 meters per second. And the minus sign would say that it's moving to the left towards compressing it. If it was moving back to the right, it would be plus 0.87 meters per second. The question just says how fast is it moving, so we can just say the speed is 0.87 meters per second at this point in time. So There are a lot of point ones that showed up in that when we did it numerically, but the interesting thing is that uh, the speed is 0 when the displacement was 10 centimeters. And when the displacement was 0, the speed was 1 meter per second. And this question says, how fast is it moving when it's halfway in between those things? So it'd be very tempting to say, oh, it's moving at half a meter per second, or maybe it'd be the square root of a half or something like that. But it's not. It's a different value. It has only slowed down a little bit. It's going to be slowing down dramatically in those last minutes of extension, the last 5 centimeters, minutes, but the last few centimeters, when it's reaching the limit, the amplitude is when it slows down the most. So it's still going almost as fast as it was at the central point, even though it's halfway out to the amplitude. And that's just because of the shape of the sine function. They have this very smooth curve at the top and change rapidly on the way down. So you have to go through, just systematically do the work. So this example problem showed us how we would go through, for example, and get the time, or sometimes called the phase, of where that oscillation is in its motion based on being given a value like x, and then using that to calculate the other values, in this case v. We could also calculate the acceleration that way. We also could have been given a problem where we're given a speed at a particular location and then asked to calculate some other properties there like acceleration, and you could do that following the same general approach of taking the inverse sine or inverse cosine of those things.